feet, so she's now 70 feet from him, right? That's when she starts walking. No? Right? 20 seconds have gone by, so he's walked 20 seconds times 4, that's 80. She started 120 feet away, but she's walking west at 5 feet per second. So in 10 seconds, she will have walked to here. And isn't this the instant in time we're talking about? This is the instant. So at this instant, this is where I'm going to draw my line between them. I'm interested in knowing something about, I'll use h this time. I don't know why I'm using h. Okay, I'm just going to use h. Anything about what we're given or what we want? Given or want? Speed of what? Yeah, we have both of their speeds, don't we? So we're given something and we want something. How about what we want? Maybe we start with that. What do we want? dH dt, right? We've labeled h on there. We want dH dt. We want to know how fast it's changing. We want to know it at the exact moment. At when?
20 seconds.
20 seconds, right? At 20 seconds. All right. But, okay, yeah, at 20 seconds. I'll just do that. Okay. Now, this is my instant in time, isn't it? This is my instant in time. I need a general picture. Right? I need a general picture. So these are my 3 pictures kind of giving me a feel for what's happening. Here's my general picture. In general, would you agree with this? That we've got a man that's moving in this direction, and we can call that M. And we've got the woman who's moving in this direction, we call that W. I call it X and Y if I want. Right? They're moving, he's moving, she's moving, right? So our H is still between them. But if I draw my picture like this, I can tell you how fast M is changing. M is changing at a rate of what? 4 feet per second. Right? I can do that. dm dt is equal to 4 feet per second. Ooh, and now the very important one. D what? dw dt, that's the woman's speed. And now the drum roll. -5 feet per second. Why is it negative? Because this distance W is shrinking, not growing, right? So M is growing, right? As he walks, M grows. But as she walks, W shrinks. Started at 120, got smaller. So these little arrows I put on here are kind of representing that negative there, right? All right, so we have M, W, we know how fast they're changing. We want to know how fast H is changing. We said at 20 seconds, didn't we? But we can actually change this now. Because at 20 seconds, do we know what M and W are? Yeah. At 20 seconds, what was M? 80, right? And W is 70. See, we already did that work. Because if we come up with an equation, plugging 20 seconds into it isn't going to work because our equation doesn't have seconds in it. But we can use the 20 seconds to figure out what their distances actually are at that moment in time. All right, it's equation time. This is a nice equation. I hope it's nice for you. Is it a nice equation? You need to relate what variables together? All of them. M, W, and H. All of them have to be related. Pythagorean. Look, this is a right triangle, right? Pythagorean. A squared plus B squared is C squared. So there's no law of cosines or anything here. Just W squared plus M squared equals H squared. That's our equation. And now we differentiate with respect to time. 2W dW dt plus 2M dm dt equals 2h dh dt. I think that's as far as I'm going to go. I'll talk you through the rest of it, but we're trying to solve for dh dt, right? Does it appear? Yep, it's here. Okay, happy to see that. We know dm dt and dw dt, so we've got that. We've got that. We're happy to see that. Do we know w at the instant in time? Yes. Do we know m at the instant in time? Yes. Do we know h at the instant in time? Not directly, but we can fix it now, can't we? We can fix it, like we can be it at 20 seconds later, and you can solve for h because you have two sides of a right triangle, right? So we know a squared plus b squared is c squared. So h should be the square root of whatever 80 squared plus 70 squared is, whatever that is. So could you plug everything in now? Get it? Also, be careful when you plug in dw dt. You got to plug in the negative, right? Okay. Any questions on that? I'm going to stop and I'm going to go to the next problem. So I'll put the problem up here. You can read it. There it is. Almost the same problem, but it's not. What's different? She's not going to walk west. She's going to go south. All right? Very slight difference in the wording there. Huge difference in the setup. We still have at 1 o'clock what's happening. I'll try and go a little smaller over here. At 1 o'clock, he's here, she's here, still 120 feet between them, right? 10 seconds later, what? 10 seconds later, where's he? He's gone up to 40 feet, and she is still 120 over here, right? But then 10 seconds after that, he's now 80, but she has gone south, right? By how much? 50? Right? She's now gone down 50 instead of over. So that's a different sort of problem, isn't it? So again, since I took the time to put the animation together, I'll at least play it. He starts walking. 10 seconds after he starts, she's going to start heading south, but she's going to walk a little faster than him. Right? Why do you think she's walking faster than him? Mute. Okay. Okay, and then right at 20 seconds, that's when we want to know how the distance between them is changing. So I'll back it up just a little bit. Okay, right to about there. He's been walking now 5 seconds, 7. Here we go. She's going to start heading south, and now that distance between them is changing, right? And at exactly 20 seconds, which is about to happen, that moment, right, I missed it, right? I missed it, I missed it. Right at that instant, at 20 seconds, how fast was that distance changing? All right, let's try and put a general picture together here. This is the instant in time, right? This is the instant. So let's call that, let's use a letter we haven't used. P, okay, P. We want to know how fast P is changing with respect to time. Agreed? So we want dp dt at exactly what? Yeah, so this is where we say 20, we can say 20 seconds again, at 20 seconds. The reason I can't say at like m equals something and w, because we haven't labeled anything yet. We need our general picture to assign a variable, then we can come label it. So our general picture is basically some guy walking north and someone walking south, like that, right? M is growing, W is growing, but down, right? And then our P is the thing connecting the two, like this, P. Do y'all agree? So right now, could I change this, now that I've assigned variables? Could I say instead of 20 seconds, I could say M is and W is? What would M be? So we're looking at that picture right there, 80. And W is 50. We have not written down what we were given. dm dt, how fast a man's walking, that's 4 feet per second. And then how fast the woman is walking, 5. So is it going to be 5 or is it going to be -5 this time? Why is it +5? Yeah, because the distance between them is growing, right? If you put -5, that would mean she's walking with him, which is kind of strange, but he would be going like this and she would be catching up to him eventually because she's walking faster than him, or catching up side by side. All right, we need an equation. We need an equation. Anybody have a good equation that would relate P to M and to W? Yes?
Could you do like the Pythagorean theorem thing again? Because isn't you,
Like a right triangle again?
Yeah.
Uh-huh.
Aren't you 130 this way, and then is it 120?
Okay, so you're saying we could do Pythagorean because you know that this is 130 and this is going to be 120 still, right? Yes, I agree, but we need to do it off that picture, not this one. So stick with that same thought.
So you could do m plus
There you go.
squared
So
plus 120 squared.
what Jackson's seen is this right triangle right here. Y'all see that right triangle? We know that this distance from here to here is whatever M is plus whatever W is. This is M plus W. And what is this distance? 120. And that's not changing, right? And now you have a relationship. So we know, you're saying, Jackson, it's M plus W squared, right? Plus 120 squared equals P squared. We just need to be careful on the M plus W squared. We have to put it in parentheses, all right? There's our equation. It's whatever this side is, which is the M plus the W, and then square that side. Questions on the formula?
Can you explain that one again, please?
Okay, so it's easier, I think, if you look at this first. If I ask you what the distance is from here to here vertically, you would say 80 plus 50, right?
Right.
Okay, but if this was M and this was W, then you would say it's the M plus the W, right? So if we look at this, if I want the distance from here to here, right, it's the M plus the W, but there's a triangle right there. So this whole side is M plus W. This whole side's 120 because that was given to us. One's going north, the other one's going south, so 120 is not going to change. And then P is the hypotenuse of the right triangle. So we got A squared plus B squared is C squared. I'm going to take the derivative right now. I'm not going to FOIL that out or anything. Just going to take derivative. I'm going to use a chain rule. So the derivative of this squared would be 2 times M plus W to the first power, I don't need that, times derivative in here, right? dm dt plus dw dt. So I'm having to take derivative of each one separately because there's addition between them. I'm done with this, right? Plus, what's derivative of 120 squared? 0. So that's gone. Equals 2p dp dt. All right, and I believe everything there we're happy to see. We know m at the moment in time?
Yes.
We know w at the moment in time? Yes. Right, 50. dm dt, 4. dw dt, 5. dp dt we're looking for, right? That's what we're trying to find. P we don't know right off the bat, but we can find it because we can complete this triangle right here. And like Jackson said, this 80 plus this 50, right, would be 130. So we have a triangle that looks like this, 130, 120, and P. And so you could go and solve that for P. And once you have P, you plug it back in here, and you're in business. Okay. I think at this point, we've done what, 3 problems now? 4 problems? 4? The only other one that I would be interested in doing is the plane flying overhead. You know what? I think that's in the homework. No? Did someone say that was in the homework? Yeah. I'm going to leave that to you then, because I worked through it in the homework solutions. So I'm going to say we're done with related rates. All right? I think for now, it's just going to be down to you doing your homework, because all these problems are just different in their own respect. So you have to be able to read them, interpret, but they all have this same sort of basic idea. All right.
So are there going to be more problems where we're going to have to like try to figure out that we have to split a cone open or something?
I'm trying to think. In the homework problems, there's not a whole lot. There's a problem where they have a gravel pile that they have a conveyor belt that's dumping gravel onto a pile, and it's shape of a cone. But they tell you in there that that cone, like, you know, when you like dump gravel into a pile, it gets wider and then it gets taller at the same time. They give you like what those proportions are. I don't believe in that problem. You have to cut anything open. But you might. I'll have to go back and look at the problem. So,
Well, I wasn't asking so much about the fact of just having to cut a cone open, but like
Yeah.
having to figure out that we have to either cut a cone open or do a circle or like something like that.
yeah. Yeah, they're all going to have some unique sort of formula that you'll have to derive from it, you know, and that's part of the challenge for you, is to draw things out and be like, oh yeah, this is a right triangle, like you use Pythagorean, or oh, this is a law of cosines, or this is similar triangles, because if I cut it, you know. So if you start playing with the homework problems, you'll start to see that every one of them is kind of unique, but they're all similar. I hope that makes sense. Yes, sir?
For this problem,
Uh-huh.
what if seeing the big triangle is 2 little right triangles as well, right?
Are you meaning like you could have looked at it as like this and this? I don't know if that's what you meant.
No, well, the upside down, for the other triangle. Do Pythagorean theorem for both of them at the hypothesis.
But you wouldn't know
You wouldn't know P. Yeah, you wouldn't. There's a couple of things you don't know. Like, you don't know what that is. Like the distance from here to here, you don't know what it is.
It's not 60.
Well, no, because you don't get to control where they are. In the general picture, you don't control where they are. There would be a place where they would be 60. Would there? I don't. You know, I don't think there would. But either way, you can't fix it. So this would not. I think algebraically you could still do it, but it would just be much more difficult.
Okay.
Yeah.
You could see it though as proportionals, right? Like the m as one side, and then m plus w is on the other side.
Proportions and
Like the red triangle and then a little black outline triangle that you have.
That those are similar, you mean? Yeah. But you don't know what that is, right? That's the thing. You still don't know what that is. I mean, you could write it as 120 minus some variable, but that's always changing. So I did have another question on this one. Well, we never got an answer here, right? We never worked it completely out. Did anyone do it by chance? No? You did? Did you get a numerical answer? What did you get?
6.61 feet per second.
6 point what?
6.1.
6.61 feet per second is the answer we got for after they'd been walking for 20 seconds, or 20 seconds have gone by. How fast was he going? He was going straight up at 4, and she was going straight down at 5. So if they had started like this, he goes like that, and she was right below him, and she started walking away, what would be the distance, what would be the rate of change between them? 9, just 9 feet per second, right? They're back to back, they start walking away from each other. That speed, the rate at which the distance between them is increasing is constant because they're opposite directions, right? 9. So let's say we go 20 seconds in, this is how fast they're moving apart. What about 100 seconds in? Do you think this number is going to get bigger or smaller? So let me try and, at 20 seconds, how far had he walked? 80? And then she had walked, I think we said, what was it, 50? Okay, and we were trying to find the rate at which that distance between them was coming apart, and we said 6.61. I'm saying, what about way, way down the road, maybe 100 seconds later? This picture, what would change in this picture? He would be way further and she would be way further down, right? But this width wouldn't change. So it would look now like something like this. And now the distance between them, we're talking about that line, right? Yes? Like I've drawn it so that's 120, that's 120, right? He's gone real far, she's gone real far. So do you think that that is coming apart faster or slower than it was here? What about a year later? Okay? A year later, what would this look like? He would have gone like this. She would have gone way down. And what about the distance between them? It's going to look almost like nothing, isn't it? So it's going to be like, here's 120 now, right? Like that. But she's way down here. So if I connect that to that with a straight line, it's almost what? It's almost vertical. It's almost like they're back to back. Does that make sense? Does it make sense?
Yeah.
So as time goes on, this number should get bigger and bigger and approach 9, but never go past 9. Does that make sense? Because it can't go past 9. 9 would be the limit because they can only go as fast as they're walking away from each other if they were back to back. So this will asymptotically approach 9. You could almost look at it like this. If this is time, right? As time goes on, here's 9. It's going to approach 9 asymptotically. I'm just wondering if, I doubt that crossed your mind, but I'm curious. If you start analyzing these things a little more, you start to uncover these other little details. And what's amazing about it is that the formula will show that. Watch. Sorry, I'm too deep in now. It was 2w plus m, I have it backwards, it's okay. dm dt plus dw dt equals 2p dp dw, right? Dt, sorry. Yes, that was what we got when we took the implicit differentiation? Okay, so I'm just going to do a couple things here. I'm going to get rid of 2. I'm going to get rid of 2 because that can go away. And let me solve for dp dt. So I'm going to have w plus m dw dt plus d. Well, you know what? Let's do this. Do we know what these are? What are those together? 9. That never changes, right? So this side's really 9 times this over Oh, this is freaking beautiful. This is why I love math so much. This is just absolutely beautiful. Watch. I'm going to divide both sides by p. Okay? Divide both sides by p. Now, as they walk away from each other, right? That triangle that we drew, right, is going to look like this. Like, here's my right triangle, right? It's going to look really tall and not very wide, yes? So W, or this is M and this is, well, M plus W, right, is this distance from here to here. Isn't M plus W basically P? I mean, it's not, right? But this was M plus W, and P was the hypotenuse. So I got to draw it again. Here's our triangle, right triangle. There it is. After a lot of time has passed by, there's our right triangle. This side's P, and this side's M plus W. As time goes on, right, the limit as t goes to infinity of M plus W should be what? As t goes to infinity, M plus W approaches P, doesn't it? They basically become the same thing. Never gets there, but it'll be basically the same thing. So in the limit, if I let t go to infinity here, this goes to P. And P over P is 1. 1 times 9 is 9. So in the limit, if you take time to go to infinity, this quantity approaches 9. Math will never fail you like that. It always matches what your logic is going to tell you is going to happen. It always works that way. Okay, we have to move on. All right, so what I'd like for you to do over the weekend, of course, do your related rates homework, but I'd like for you to also go back and review exponential and logarithmic functions. This is college algebra stuff. I'll talk a little bit about them next class, but I want to just get right to it, like right away today, just right to what we need to talk about, which is going back to derivatives, before implicit differentiation, right? Before implicit, when we were just doing standard derivatives. Hey everyone, y is equal to x squared. What's y prime? And everyone's like, 2x, yay. And everyone loved that, right? We're going to kind of go back to that now. The question is, if y is e to the x, what's its derivative? Okay? We have not talked about that. We have talked about how you take the derivatives of things raised to powers. We've talked about if you have things multiplied together, product rule, quotient rule, chain rule. We know derivatives of sine, cosine, tangent, all these things, right? And we have conveniently avoided this, haven't we? We've stayed away from it, right? So today we get to talk about it. So before I tell you the answer, I want us to make sure we understand what that function is, right? So the function e to the x, you learned about that in college algebra, don't you? And you learn about this function when you're talking about exponential functions, right? They're like, okay, there's this whole class of new functions, everyone, and they all look like this. F of x equals a raised to the x. And they tell you all exponential functions look like this. And they give you some conditions. They tell you, oh, that a down there, it can't be 1. And they also tell you that the a down there has to be bigger than 0. Say as long as that number is positive and as long as it's not 1, then you're talking about an exponential function. So examples would be like 2 to the x, right? 4 to the x, 10 to the x. And when we graph them, they look like this. They either are going to grow exponentially like this, or depending on the number, like if you plug in 1/2 right here, 1/2 to the x, It might be a reflection over the y-axis and go like that, and that's like exponential decay. So you have these two ideas from college algebra. That's why I'm saying go back and review this a little bit over the weekend if you need to look at like what their graphs look like. But at some point in the college algebra class, they said, hey, you know, look, there's this very special one. Did they tell you that? Did somebody tell you that e to the x is a very special one? They didn't tell you how special it was? No? They just said, here it is? Really? They should have like delivered it gift wrapped, all pretty bows and balloons and stuff, no? Okay. Well, it's special, all right? So e to the x is known as the natural, not log, natural exponential function. The natural exponential function is this one, f of x equals e to the x. But e is actually just a number, okay? E is just a number, because to be an exponential function, you just have to have a number here. It has to be bigger than 0, and it can't be 1. So e, right, is some weird magical number that they put here, and they tell you, do they tell you what e is? They tell you it's like 2 point something, like they tell you like e is approximately like 2.718. Like, why don't they just tell you what it is? Why do they have to give you an approximation? Why don't they just tell you what it is? Because it's irrational, like pi is. And it never stops. This right here keeps on going forever. It never stops, never repeats. Okay, so there's no pattern to the decimals. So they can't give you anything better than a letter to represent it. And in mathematics, anytime we give a number a letter, that means it means something. Like pi and e, like those are very special, so they get letters, all right? All right, so you got this special function. Nobody asked back in college algebra, like, why is 2.718 blah, blah, blah to the x, why is it so special? Right? I mean, no one asked? Don't ask those types of questions. Okay, so here's why this function is so special. So if I graph it, it'll look like this, right? We know it looks like exponential growth because this number is bigger than 1. So we know it's growth. And in a calculus class, we are doing slopes of tangent lines, right? Derivatives. Okay, so let me just ask you right now. If I asked you to take the number 0 and plug it into this function, what would you get? What's f of 0? Would be 1, all right? So that means at 0, I go up 1, I put a dot, right? Okay, what would f of 1 be? So if I plug 1 into this function, I would get e to the first power, which is just going to be like 2.718. So that means when I go out to 1, this is not drawn to scale. If I go out to 1, then I'm going to be up at like 2.718, okay? And what about if I go out to 2? Where will I be at 2? So you got to square it, right? What is it? Someone got that for me? E squared as a decimal, 6 point something, I think? 7? 7.389, something like that, okay? So far, nothing special, right? Nothing special. Now, we come in as calculus students. We say, all right, let's say I wanted to go to 0 and I wanted to know the slope of the tangent line there, right? What is the slope of that tangent line at 0? What's the slope of that tangent line at 1? And what's that slope of that tangent line at 2, right? That's what I want to know today. So I'm asking, what is the derivative? What's the slope of this tangent line at 0, right? Well, guess what? It's that. It's 1. And if you want to know what the slope of the tangent line is at 1, guess what? It's that. And if I want to know the slope of the tangent line at 2, guess what? It's that. Which means that the y-coordinate of the graph is also the slope of the tangent line at that point. So what is the slope of this line? On the e to the x function, what is the slope of that line? 1. What is the slope of this line? 2.718. What is the slope of this one? 7.398. Okay? The slope is actually the y-coordinate. And guess what? It's the only function that exists that behaves like this. There is no other one. This is the one. And the way it worked historically is that what we did is we said to ourselves, I mean, can't you from this just say, look, what we're saying is that the derivative at 0 is equal to the function at 0, right? The derivative at 1 is equal to the function at 1. The derivative at 2 is equal to the function at 2. In other words, the derivative, right, is equal to the function itself. And so, historically, what we were doing is thinking human beings is we were like, I wonder if there's a function out there that is its own derivative. I wonder if it exists. We were looking for it. We went searching for it, and we found it. And this is it. This is the only one. It's unique. So that's why we call it the natural exponential function, because it is the one that naturally occurs. It's the only one, okay? It's the only function that is its own derivative. Does that kind of make sense? If you take the function x squared, right? That kind of looks, kind of like that, right? Parabola. But let's say we go to 1, right? We plug in 1. What do we get when we plug in 1 here? We get 1, right? So the y-coordinate's 1. What's the derivative of that function at 1? 2. So the slope of the tangent line here is 2. The y value is 1. They don't match up. This one matches everywhere along the entire graph. The y value is always equivalent to the slope of the tangent line. Okay, I'm going to run out of time, so I can't get too much more into it, but what I'm telling you is that the derivative of e to the x is e to the x. Right? That's what I'm telling you. I'm going to show it to you one more way, and then I'm going to let you go because we've had so much fun today already. You will learn in Calculus 2, if you take Calculus 2, you will learn that e to the x can also be written a different way. It can be rewritten this way. 1 plus x squared over 2 plus x cubed over 3 times 2 plus x to the 4th over 4 times 3 times 2 plus x to the 5th over 5 times 4 times 3 times 2 plus x to the 6th over, I'm going to stop here, 6 times 5 times 4 times 3 times 2, and this actually goes on forever and ever. So if you go to your calculator right now and you type in e squared, what your calculator does is it replaces that with a 2, 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 and somewhere in the programming of your calculator, it stops, and then it adds all that up and it gives you the answer. Okay, that's what your calculator is doing. But I want to show you what's so freaking beautiful about this. If you can just take on faith that that's e to the x, can you take that on faith right now? I'd like for you to take its derivative. Okay, what's the derivative of 1? 0. What's the derivative of x? Plus, okay, derivative of x squared over 2. So what happens? 2 comes out, cancels with the 2, and what do you have? X. Okay, plus, next one. 3 comes out, cancels, and what are you left with? X squared over 2. Okay, plus this one, 4 comes out, cancels with the 4, what are you left with? Over 3 times 2, right? Plus x to the 4th over 4 times 3 times 2, last one. X to the 5th over 5 times 4 times 3 times 2 times, and what is this? It's the same thing. Same thing. Right? It's the only function out there that does it. There's nothing else. You'll never find another one. All right? All right. Y'all have a great weekend.
That means the second derivative.
And that means the second derivative of it is itself. The 1000th derivative of it is itself. Yep. What now? I thought I heard a question. No?
He was talking about this Spanish.
About the what?
No questions.
No questions? Okay. Do your relation.